In most retro computing tales, the Motorola 68000 is the star of the show. It powered early workstations, iconic home computers, and a whole generation of arcade boards. But sitting just off to the side is a quieter sibling, the Motorola 68010. On paper, it fixed some of the 68000's rough edges, ran a bit faster, and added features computer scientists had been asking for. Yet, it never became the default choice, and today it's almost a trivia answer rather than a legend. This is the story of that overlooked chip. Why did Motorola bother designing the 68010? What did it actually improve? And why did so few systems adopt it? The answers sit at a crossroads of engineering detail, operating system theory, and plain old business timing. And they reveal how even a technically better part can slip into the margins of history. To understand the 68010, we have to start with the world. The 68000 created around 1979 to 1982. When Motorola introduced the original 68000 at the end of the 1970s, it stood out. It offered a clean, orthogonal 1630 seconds of a bit architecture with a 16-bit external bus, a large linear address space for the time, and a programmer-friendly instruction set. Compared to 8-bit and early 16-bit CPUs, it felt like a small mini-computer on a chip. By the early 1980s, that made it very attractive. It showed up in early workstations from companies like Sun and Apollo, where developers pushed it hard with Unix-like operating systems. Arcade and pinball manufacturers embraced it for their high-end boards, needing more power for graphics and game logic. And just as important for its later fame, the 68000 family would anchor the original Apple Macintosh and the era of Amiga and Atari Saint machines, even if those home systems actually arrived slightly after the 68010's debut. In this period, the 68000 built a reputation as a flexible workhorse. Toolchains, compilers, debuggers, and operating systems were all tuned for it. That success set the expectations and the constraints for whatever came next, including the 68010. Motorola announced the 68010 in 1982 as an evolution, not a revolution. At a glance, it was pin-compatible with the 68000 and designed as a drop-in replacement in many designs. The idea was simple: keep the architecture and instruction set almost identical, but address a few shortcomings and squeeze out more performance. One of the most talked about changes was loop mode. The 68010 could detect certain tight instruction loops and execute them more efficiently by avoiding some of the usual instruction fetch overhead. In practice, the benefit depended heavily on the exact code, compiler, and workload, but it was the kind of micro-optimization that mattered to performance-conscious workstation and embedded developers. The more profound change was about robustness in the face of faults. The original 68000 had trouble restarting complex instructions cleanly after a bus error or a page fault, which limited full-featured virtual memory. The 68010 added an extended, or long, bus fault stack frame. In plain terms, it stored enough internal state on the stack so that after an interrupt or fault was handled, like a page of memory being loaded from disk, the CPU could reliably resume the interrupted instruction as if nothing had happened. There was also a subtle but important privilege change. The move from status register instruction became privileged on the 68010. That helped operating systems enforce protection models more strictly. And overall, thanks to minor internal tweaks and timing improvements, the 68010 generally ran a bit faster at the same clock rate. Though exact performance figures vary by source and benchmark, and contemporary documentation doesn't always agree on the typical percentage gain. The extended fault handling in the 68010 was largely about one thing: making true virtual memory feasible. In theory, that was a big deal. With solid support for restarting instructions after a page fault, an operating system could implement demand paging, like on larger Unix systems. Programs could see a large contiguous address space that didn't have to be fully resident in RAM. The CPU would trap when it touched a missing page, the OS would load it from disk, and the processor would continue as though nothing unusual had happened. On paper, this pulled the 68K line closer to the minicomputers and mainframes of the time. For workstation vendors and OS researchers, the 68010 looked like a more serious platform for Unix and similar operating systems than the $68,000. It answered a practical complaint they had with the original chip. But in the world of home and personal computers, this capability mostly sat unused. Machines built on the 68000 and 68010 in the early to mid-1980s typically shipped with limited RAM and used single-tasking or cooperative multitasking operating systems, without demand-paged virtual memory. For those systems, the ability to restart complex instructions after a page fault was irrelevant, because the operating system never generated those page faults in the first place. The most visible benefits of the 68010 became confined to niches where Unix-like environments or sophisticated multitasking actually ran. So where did the 68010 actually find a home? It did ship in certain Unix workstations and development systems. Sun Microsystems, for example, used it in some early models as part of their move from the 68000 toward more capable processors, pairing it with Unix variants that could take advantage of its virtual memory support. Some industrial controllers, data terminals, and arcade or gambling machines also used the 68010 as a modest performance upgrade over the 68000, while keeping existing board designs. One more visible consumer example was the Sinclair QL, launched in the mid-1980s. The QL used a variant called the 68008, or, in later or derivative designs, a 68010 class CPU, aiming to bring a 32-bit style architecture to the home and small business market. Even there, though, the benefits of the 68010's virtual memory features were not fully exploited in mass-market software. The 68010M often appeared as an upgrade path, rather than as the heart of brand-new high-volume machines. For many manufacturers, the entrenched 68000 ecosystem was simply good enough. Boards were already validated, software was tuned, and core-sensitive markets didn't welcome even small increases in bill of materials pricing. For a modest speed bump and some OS-level features that few products needed, redesigning for a 68010 could look like unnecessary risk. At the same time, the competitive landscape was shifting quickly. By the early 1980s, Motorola and its rivals were racing toward more advanced 32-bit processors. For Motorola, the real destination was the 68020, which arrived around 1984. It expanded the instruction set, improved performance much more dramatically, and laid a foundation for features that would define later 68K generations. Inside Motorola, the 68010 functioned as a stopgap, a way to address immediate complaints about the 68000 and keep workstation and Unix customers satisfied while the 68020 was finished. Once the 68020 was on the market, the 68010's window of opportunity narrowed quickly. System designers looking to the future often chose to leap straight from the 68000 to the 68020, especially for high-end or forward-looking products. Meanwhile, Intel, National Semiconductor, and others were advancing their own 16 and 32-bit lines, and RISC designs were emerging in research labs and early products. In that environment, the incremental improvements of the 68010 seemed less compelling compared to larger architectural jumps. The business logic favored investing in the next big step rather than extensively promoting an intermediate part. Today, when people reminisce about 68K systems, they usually talk about the 68000 that started it all, or the more advanced 68020 and 68030 that powered later workstations and higher-end machines. The 68010 sits quietly between them, remembered mainly by collectors, Unix historians, and those who enjoy tracing the detailed evolution of CPU families. As a piece of engineering, it solved real problems. It made virtual memory practical, tightened up privilege handling, and offered modest performance gains without breaking compatibility. But history shows that these kinds of incremental improvements don't guarantee adoption. When software ecosystems are already stable, and a bigger leap is visible just ahead, a carefully refined middle child can be left with only a small slice of the market. That's the curious legacy of the Motorola 68010, a capable processor that nudged the 68K line forward, but rarely got to be the star of any system. In the crowded cast of 1980s microprocessors, it played its part, then quietly stepped aside, leaving most of the glory to its more famous siblings, and a subtle trail of design lessons for anyone willing to look back and notice it.